Hello, everyone, and welcome to the electrochemical colloquium. Today, we're discussing the electrical double layer at the electrochemical interfaces. As we all know, the double layer is absolutely central to any electrochemical processes. So still, despite this importance of double layers, the structure and the dynamics of the double layer for even the simplest systems is quite poorly understood. And the analytical theory of the double layer seems to be impossible to develop. Today, most researchers use the numerical calculations trying to model the double layer and predict the electrochemical processes. But are such models close to the reality? And what is the future of this field? This is what we're going to discuss today with our speaker, Professor Wolfgang Schmickler, who's a leading theoretician in electrochemistry and metal electrolyte interfaces. Wolfgang received his PhD in 1973 and then habilitation in 1978, both from the University of Bonn in Germany. Later, he worked at the University of Düsseldorf, State University of New York, and Utah State University. And since 1992, he is a professor in the Institute of Theoretical Chemistry at the University of Ulm in Germany. So Wolfgang, thank you so much for joining us today. We're really looking forward to your talk. Now the stage is yours.
Okay, Andrew, thank you so much for the introduction and for giving me the opportunity to talk at this nice symposium series. I shall go to my presentation and let's hope that it all works. So I go to, and now, I think it was too early, right? First, I have to share the screen.
Yes, first share the screen.
Mm-hmm. And now I must find the presentation in whatever.
I think you're not sharing the screen yet.
No? Yeah, because I haven't found, there's a long list, which I see here. Here it is, Keynote. Mm-hmm. And now you ought to see it.
Yes.
Right? And now I go to presentation mode. And now everybody ought to see it, okay?
Yes. Mm-hmm.
So we are all set up. Okay, good afternoon, ladies and gentlemen. So like Andrew said, we're going to talk the double layer at the metal solution interface. Let's see. Okay. So like Andrew said, the double layer is really the heart of an electrochemical system. That's the region where everything happens. Electron transfer, proton transfer, deposition, dissolution of metals, formation of layers, corrosion, passivation. So this is really the central part, and it's the most difficult part, of course, of the system to handle, because you have the interaction of two different phases there. So, of course, in several talks in this symposium, the double layer has already been discussed. So it is not a completely new topic, but I think this is the only talk which is only devoted to the double layer at metal solution interfaces. So right at the start, there's no universal model or no universal theoretical approach to the structure of the double layer. And I hope this is going to come clear during my talk. So this is the picture which we have taken from our own textbook from Sanders and Schmickler. And really, this is a very simple picture, even though it's still more complicated than the traditional Gouy-Chapman Stern model. But you have, of course, it's called the solvent. We have ions of various sizes. You can have various reactants. And of course, the electrode surface doesn't have to look as nice and plain as the single crystal surface that we have painted here. So it's a complicated system, and we'll see what we can understand about this. So this is the menu, and the first and most important and longest part of the talk is, what does the double layer not look like? Okay, and then we shall become somewhat more constructive, and we'll of course go through the Gouy-Chapman theory, which should be familiar to everybody, and then explore some little known consequences for adsorption at low concentrations, a topic which seems to have come back last year and which we treated in the 1980s. So then we say something about classical density functional theory, which has often been applied to the double layer, and something about technique which I have used with a colleague, with Doug Henderson during the 1980s, which was based on DFT and integral equations. And I still like it because it teaches you many things about the double layer, which somehow get lost if you use some version of DFT. And I hope you're going to like it as much as I still like it. Then we go to simulations, classical, DFT-based. Of course, we have had the talk of Axel Gross about the DFT-based simulations. So I shall be short on this. And then at last, something about the time dependence, which seems to be a neglected topic. And it is something which is called the relaxation of the double layer as or while a certain electrochemical process happens. And I think this is important and overlooked. So this is the menu. Yeah, of course, there are many interfaces where a double layer of equal and opposite excess charges exist. And they usually form between two conducting phases. And there's a short, but by no means exhaustive list. Right. So in all of these cases, we have the formation of a double layer of equal and opposite charges, which are separated, so that you have a dipole potential drop as you pass through the double layer. So we are going to focus on the metal solution case. Yeah, there are two limiting cases which I discussed. One is traditionally called a non-polarizable interface. And this is a phase in which the two phases can exchange at least one charge carrier. And typically this would be an electron. And then the potential difference and the excess charges on both sides, they are then determined by the difference in the electrochemical potential of that particle in both phases. Of course, there can also be systems where more than one charge carrier can be exchanged. And in this case, we have something which is something like corrosion, which we're not going to cover in this talk, but this would be a nice topic for some other talk. So there is the other, okay, so this is the simplest case where we have two metals, which have a different work function. And the negative of the work function is the same thing as the electrochemical potential. Then when you bring the two in contact, they can exchange electrons. The Fermi level becomes equal in both these metals. And then you have an exchange of charge, and you have a double layer forming here. And this double layer gives then rise to a difference in the external potential. And the difference in the outer potential here simply cancels the difference in the work function. And the whole concept is practically the same thing as the Nernst equation for an aqueous solution in contact with the metal. So this is the case which we are not going to treat today, but we shall look at something which is called the ideally polarizable case, where there's no exchange of ions or electrons. And this you can usually see in a cyclic voltammogram. And this is the case of gold 111 in a solution of HCl4. There's a large range here where nothing happens. So in this range, you can apply a certain potential difference between your working electrode and your your reference electrode, and nothing much will happen in terms of reactions. And this is the classical case, and something which has been intensively investigated since the time of Gouy and Chapman. So this is the case we are going to look at. So we are going to consider a model for the ideally polarizable metal solution interface. So let's see. I shall start with my least favorite double layer models, because I think it's important to point out that they're still being used often, but they are really terrible. So let us look. There's this flip-flop model, which came out sometime in the 1970s. There's the Bockquist-Devenath and Müller model. There's still the model of the ice-like layer or bilayer, sometimes being used. And there's a terrible page on Wikipedia. And at some time, one of us, perhaps I, perhaps somebody else, has to change this page in Wikipedia because it's terrible, and it makes a terrible impression for our field of study, terrible impression for electrochemistry. So let us see. Yeah, this is the flip-flop model. The assumption is that water, which has a dipole moment, can take up only two different orientations at the surface, dipole up and dipole down. And if you go to negative charges, all of the positive ends here are going to point toward the electrode surface. If you had positive charges, the opposite, the negative end points toward the electrode. If you had the potential of zero charge, and then you have alternate orientations of the dipole. The only advantage of this model is that the mathematics are easy. You can simply map it onto an Ising model, and you can use all of the methods one has for the Ising model. But obviously, this is not a realistic model for water in contact with a metal surface. And keep in mind, if you would have such a fully oriented layer, this would give rise to a potential drop of the order of 7 to 8 volts, which of course is impossibly large for water and for any other solvent. So let's get rid of the flip-flop model. Yeah, the next one, which I also hate, is the Bockquist-Devenath and Müller model. It also has the flip-flop for the first layer of water right at the surface. It has, in this picture, the perfectly solvated cations, and they have the diffuse layer at a larger distance. And one of the things that I do not like is a locally varying dielectric constant, because the dielectric constant is not a local property. You need to have at least a mesoscopic ensemble in order to define and to calculate the dielectric constant for a system. But here it changes from 6 in the first layer to 30 in the second layer and 80 in the third layer. Of course, it is easy to make calculations with such a simple model, but that does not make them realistic. So let's get rid of Bockquist-Devenath and Müller. So yeah, the next one, which was a bit popular during 2005, 2010, and a little bit later, was simply to model the water in contact with the electrode surface as a bilayer of what is really ice. So this would be the case for platinum, and this picture has been quite popular for a certain number of years. But such a bilayer exists only in ultra-high vacuum at temperatures below 120 Kelvin. And these are not the conditions in which electrochemistry has been practiced. And there was a nice paper by Schnur and Gross who showed that such a bilayer is not stable at room temperature, not even on platinum, where the interaction of water with the surface is somewhat stronger than the interaction of water, say, with silver or with gold. So this is the reference if anybody wants it. So let's get rid of the bilayer. Good. Sometimes you can also read there some speculation that the first layer of water in contact with an electrode surface would be an ice-like layer, which would be quite firm. But if you'd have such an ice-like layer, then electrochemical reactions like the deposition of metals or the adsorption of ions could not take place, or they could take place only with a high energy of activation, because they would have to pass through this ice-like layer. So obviously this idea is not very good. And in fact, the deposition of silver, which would have to pass through such a layer, is one of the fastest electrochemical reactions. So definitely this is also one of the wrong ideas about the double layer, which had also been popular for some time. Yeah, this is a page from Wikipedia, which I said is a shame for electrochemistry. Right? You also have this stupid layer of all of the water molecules pointing into one direction. We have the perfectly solvated ions, and then you have the geometrical distance. You have geometrical distance 1, which is the inner Helmholtz plane. Second one, which is the outer Helmholtz plane. For me, it's a terrible and terribly oversimplified picture. So let's burn this also. Yeah, then there's the Helmholtz model, right? Which is from 1879. And there all of the counter ions are in one particular plane, which is the Helmholtz plane. Of course, this is an oversimplified model, but I'll show you later that there is one case in which it actually holds, but this is a very special case to which I shall come later. So obviously this is too schematic, and the whole concept of the diffuse layer, which with the achievement of Gouy and Chapman, this is lacking here. Okay, let's go to the Gouy-Chapman theory, which is more than 100 years old. And yeah, I think you probably all know solution is a dielectric continuum. It contains point ions, and the metal is taken to be a perfect conductor. So as a first approximation, this is not all that bad. One can treat the electrostatics and the statistical mechanics, and one has to solve the Parsons-Boltzmann equation, which with this particular geometry can be solved exactly in an analytical manner. But this is also one of the advantages if you can really calculate something by hand and then really see what happens if you change certain parameters. One of the most important quantity is the Debye length, which is inversely proportional to the concentration of the ions. If we are looking at a 1 molar solution, that would be the order of 3 angstrom. It's a bit small. For 0.1, it would be of the order of 9, and then of course it goes with the root of the root of the concentration. So this is important, and the whole concept, the whole theory, of course, only makes sense if the Debye length, which is the range over which the potential and the concentration of particles change, if this is much larger than the diameter of particles. Right. So also it does not hold if the deviations, the potential of the charge are too large. We can see that in this case, more ions will go to the surface than the surface can actually take up, because the finite size of the ions and of the solvent are missing in this model. So this theory is the starting point of any treatment of the double layer. Experiments focus on the capacity often, because this is something which can easily be measured. And this is the exact expression which you can get within the Gouy-Chapman theory. There's a small linear region when the exponent here is much smaller than 1. Then we have this simple formula, which simply says that the interface behaves like a capacitor with plate separation given by the Debye length, which is simple and intuitive interpretation of what happens in the simplest case. Problems start as soon as the concentrations goes up and as you go away from the potential of zero charge. And here are some typical curves, and you can see the capacity goes up and up. Units here are farad per square meter, and in order to convert this to microfarad per centimeter to the -2, you have to multiply this by 100. Okay, so you can see the capacities here are much higher than anything which has ever been measured. So obviously, this is due to the fact that the finite size of particles has been neglected, and more particles can go to the surface than the surface can actually take up. So this is the problem. Let us look at some experimental curves, and these are the famous experiment of Graham. Notice that at that time, negative potentials were all plotted toward the right. And you can see if the concentration is low here, you see a nice minimum in this range. It really follows the theory of Gouy-Chapman. But then there are deviations, and they're particularly large if you go to positive potentials, where you would guess that the adsorption of anions sets in, and that is what happened. While here, it seems all fairly normal, and not much seems to happen here. Let us look at some other data. Yeah, the minimum of the capacity at the potential of zero charge. This followed from the theory of Gouy-Chapman. And here there are capacity potential curves for 3 different surfaces of gold. There's the 111 surface of gold, the 775, and the 332. And the latter 2, of course, have steps. You can see that there are different positions for the potential of zero charge. And from the difference here, you can estimate the excess dipole moment at the surface, which is caused by the presence of steps. And it's somewhat larger for the 332 than it is for the 775, which is fairly flat. So this is also the information which you can get at. Once again, you always have a region which behaves more or less as predicted by Gouy and Chapman. Then you have the deviations, particularly large when you go to positive potentials, and not quite so large as you go to negative ones. And here the shape of the curve is similar. Yeah? So probably not much happens there. But of course, here in this region, the concentration of iron becomes high, and the finite size matters, and that's why the capacity goes down. Also, as the field gets higher and higher, dielectric saturation sets in, and this also makes the capacity smaller. So this is qualitatively speaking what happens here, but not much happens in the way of electrochemistry, while here there are definite signs that you have anion adsorption. So yeah, this is then the famous Gouy-Chapman-Stern layer, which is also a model which I don't like because it's an oversimplified model, right? You have these planes, simple geometrical models. The distribution of the potential, which we shall see later is wrong. But really, what happens in this region, we have an oscillating potential, which I'm going to show you later. Since one has a special layer here called the compact layer, you can then simply, by simple mathematical argument, divide the total capacity up into 2 parts. One is the Gouy-Chapman part. The other one is then called the Helmholtz capacity, or sometimes the compact layer capacity, whatever you want to call it. And since the division is by potential, the division of the capacity is through the inverse of the capacity. But I think we should simply view this as the definition of the Helmholtz capacity. And if we calculate the Helmholtz capacity from experimental data, maybe this is going to tell us something about what happens when right close to the interface, very close to the metal surface, while the Gouy-Chapman part tells you what happens when you're at a sizable distance from the interface. So yeah, I think you should also not use this oversimplified. But like I said, the Helmholtz capacity must contain information on the double layer structure near the interface. So it's a useful quantity to have, and a quantity which you can think about what happens. So how do you determine the Helmholtz capacity? There's a method called the Parsons&Zobel plot, which is fairly obvious if you look at the mathematics. You do a plot of 1 over the experimental capacity versus 1 over the calculated Gouy-Chapman capacity. And if everything is fine, this should give you a straight line with unit slope and a positive intercept on which you can determine the inverse of the Helmholtz capacity. And unfortunately, there are very, very few cases where it works in such a simple way, but I'm going to show you at least 2. Okay, so this is taken from Parsons and Zobel. Mercury is nice because Mercury is passive. Nothing much happens there. And I think it's a bit of a pity that this has dropped out of use, but also easy to keep clean. I just simply change the drop and you have a fresh surface. But here one has for 3 different charges. One gets more or less a nice straight line with slope 1, from which you can get the Helmholtz capacity from the intercept. These are data from Validity, and these are for 3 different ions, right? And then for KPF6, which does not seem to absorb, you get a nice line of slope 1, on which you get the Helmholtz capacity. But the other ions, fluoride, perchlorate, they show distinct signs of absorption. The slope here is about 0.8, here is about 0.668. Obviously, these are deviations from the perfect behavior, showing that there must be something going on. And this is typically specific and absorption, because you can see that it depends on the nature of the anion, right? So, but for the cases of mercury and also for silver, you can get in the case where the adsorption of anion is small, you can calculate the Helmholtz capacity, and these are the curves for mercury and for silver 111. Notice there's a large difference in the capacity between silver 111 and mercury, and since in this region here nothing much seems to happen in the way of absorption, the difference must not be due to the solution, but must be due to the metal. Obviously, silver 111 has different double layer capacities or contributions than mercury, but this I shall talk about more later. If you look at the right-hand side, then you can see there are some indication of the absorption of anions as you go to higher charges. So, and now I want to a topic on which I'd worked in the 1980s and which has come up again from a recent paper which has been published in the Angewandte Chemie by the group of Mark Koper, and I think which can be explained by the weak adsorption of ions, and we shall discuss this. These are some isotherms from the group of Parsons, which had been measured during the 1970s. And this is the case where the concentration of ions is low, and he has the weak adsorption of chloride ions. And this is a nice plot, something which is difficult to get, but which I think is important. Q here, this is the excess charge on the electrode surface on mercury. And here, this is the formal adsorbed charge, the adsorbed charge, the charge on the adsorbed chloride ions. And the important point is that when you go to concentrations that are low, then the adsorbed charge is practically equal to the charge on the metal, which means that in this case, really you have a sort of Helmholtz layer, right? You have the excess charge, this case mostly positive charge, on the surface of the metal. And then right in contact with this, you have a layer of weakly adsorbed ions whose charge exactly accommodates the charge on the metal. Obviously, then there is no diffuse double layer in this case. And I think this is the only case in which the Helmholtz model actually works. But this is the special case of weak anion adsorption at low concentrations. Let's look a little bit further on this. Yeah, this can actually be proved that that this must happen. And the proof is comparatively simple. It is based on the theory of Gouy and Chapman and the basic thermodynamics. And we have first proved this in the 1980s, I think. And then at the beginning of this year, actually came back to this topic because of the nice paper by the group of Mark Koper, which I'd seen and which I think can be explained simply by our work from 1980s and some extrapolation. So this is the plot taken from the paper. It's a nice paper. Go and read it. And here he has Parsons&Zobel plots for various cases. And this is for mercury. All is in perchlorate solutions, and the slope is almost 1, which for me means that the adsorption is small. On gold 111, the slope is much smaller, and the slope is even smaller on platinum 111. And one of the things that they pointed out is that at low concentrations of the order of 10 to the minus 3 molar, in the case of platinum 111, the interfacial capacity was higher than that predicted by the Gouy-Chapman theory. This is unusual, because if you had something like a Gouy-Chapman-Stern model, the interfacial capacity must always be lower than the one predicted by Gouy and Chapman, because you have this one layer at the surface in which the ions can penetrate. But he pointed out, I think this is important to point this out, that in this case, the interfacial capacity is higher than it ought to be according to Gouy and Chapman. And yeah, the explanation in the paper, I did not find all that convincing. They claimed there was a special non-bonding interaction between platinum and ions. And yeah, I wasn't really sure what that meant, but I think everything can be explained by the simple model which I have shown. Okay, so taking this model and some extensions, you can actually calculate the isotherms, and you can calculate the Parsons&Zobel plot. You can calculate this exactly from within this model, and it's important for the case where the concentrations are low. And there's only one simple parameter which characterizes the adsorption strength. This is the difference in the electrochemical potential of the adsorbate and the electrochemical potential when the ion is in the bulk of the solution. And this is the ratio. So let us see there are two different plots. And these are the same plots like we had seen from Parsons before. Only I've used the more usual convention that the negative value go in this direction. So this is the case where the adsorption is really weak. There's only a factor of magnitude of 2 kT. And if you look, this is Q equal to 10, and this goes here not quite to Q equal to 10, but to Q equal to 9.88 or something. If you go to all of the other values, the value here, when the concentration is very low, practically, but not quite, equals the value of the charge which is on the metal. So the charge on the metal, once again, is balanced by the formal charge on the adsorbate. Here, the adsorption is a little bit higher, so it's 5 kT. And in this case, the adsorbed charge exactly equals the charge on the metal. So in this case, you have a perfect formation of a double layer, an absorbed, weakly adsorbed layer whose charge exactly cancels the charge which is on the surface of the metal. So of course we can calculate Parsons&Zobel plot, and you can see when the adsorption is comparatively weak, even when you have 2 KT, the slope goes down to 0.5. If it is higher, it goes down to 0.28. And the higher I make this ratio, then the lower becomes the slope. And then if you look at the extrapolation, then at low concentrations, the capacity can become higher than predicted by Gouy and Chapman. And I think this explains the nice capacity curves which have been seen within the paper by the Mark Koper group, without resorting to something like a special interaction of platinum with the ions. So this is something to keep in mind. This is also one of the simple cases in which using a comparatively simple model, you can get a quantitative explanation of experimental data, which is usually rather difficult within double layer theory. So that was it. So like I said, low concentration, the concentration is simply balanced. You have this double layer forming. Lower Parsons-Zobel plot is smaller than 1. And all of the data can be explained by this effect, just in the same way like the old data of Ballet and of Parsons, which had shown the same effect as soon as you have a small specific adsorption at low concentrations. Yeah, of course, this would also hold for the case we have weakly adsorbed cations, but I do not know of any example where a weak adsorption of cations has been observed, but no weak adsorption of anions. But if there is, it would be comparatively easy to treat. So let us go back. So this is the Helmholtz capacity for silver and gold. Important thing to keep in mind, this depends both on the nature of the metal and the nature of the solution. And if you want to understand this, you must have a model which contains both the metal and the solution. So something like the Gouy-Chapman theory by itself can simply not be sufficient. So let's see how I can go on, like I said, both on the nature of the metal. So what is better than the theory of Gouy and Chapman? And one must improve the situation, particularly at high deviation from the potential of zero charge, and for higher and for higher concentrations. And it must account for the effect of the electrode. It must explain why it is so much higher for silver than it is for mercury. So we shall look at 3 particular methods. One is classical density functional theory, which has become popular during the last decade or so. There's the integral equations technique, which was popular during the 1980s, which is still popular with me, and which is popular with certain Japanese groups also. And then we look at the opposite choice, which are simulations, both of the classical and of the DFT-based type. But since we had a complete talk on the DFT-based simulations, I shall be short on the DFT-based case. So classical density functional theory is, of course, similar to the quantum mechanical DFT from Sharma and Cohn, which I think is familiar to most of the audience. Here one has what is called the grand canonical potential. This consists of 2 parts. One is the free energy of the system written as a function of the density of all the particles which are within the system. Right? So rho consists of density for one ion, second kind of ion, and for the solvent also. So this is then the free energy part. And then you have a part here, and this is the external potential, which can be applied. And this can be a field, which comes from the surface of the metal. And since this is then this is a grand canonical potential, you do the calculations at constant chemical potential mu, and this is the reason why you have to subtract mu times the density here. Right? This is the way you pass from the grand canonical picture, you pass from the canonical picture, we put with this, toward the grand canonical picture by simply doing what is called a Legendre transformation, and you subtract the chemical potential, this case, time the density. So the big question is, what does the free energy functional look like? And it is usually split up into two parts. One is called the ideal one, and this is the entropy part. So this can be written in such an explicit form, where lambda is the thermal wavelength. But of course, all of the interesting part is the extra part. This contains the interaction between ions. It contains the interaction between ions and the solvent, the interaction of the solvent with each other, and the interaction with the surface. So this is the part which is the difficult part. So, like I said, this depends on the model, and this contains all of the difficult things. If you have such a density, you can then determine the densities rho of R by the usual Euler equation. So you take the functional derivative with respect to rho of R, and since this is a charge system, and it also must be a charge neutral system, this must be complemented by the Poisson equation. And if you do this, then you have a system of partial differential equations, which you have to solve, but it's not all that difficult. So there are a number of models which can be formulated with the classical DFT, and the simplest model which can be calculated or formulated in such a way is the Gouy-Chapman model. Of course, this only has the entropy part, and it has the electrostatic part, and but nothing much. There's a model which I'll talk about a little bit later, which is called the Gouy-Chapman model. And then there are a fair number of what are called modified Poisson-Boltzmann theories. There's the hard sphere electrolyte model, and there are more and more. And I cannot talk in detail about all of these models, but one of the advantages that they have, you can combine them with quantum chemical DFT. So then you have a functional consisting of two parts. One is the quantum chemical DFT part. The other is then the grand canonical part for the solution. And then the difficult part is the interface between these two, because this has to be modeled and has to be introduced into the grand canonical ensemble. But there are packages that actually do this. There's this JDFTX package. But of course, if you use it, first take a good look at what the model for the solution is and what the model for the interface is. And you must decide if you like this or not, and if you want to use it or not. But certainly this should not be used like a sort of black box with input in, output out, because this will then usually be simply garbage in and garbage out. So it has to be used with some sense. Yeah, there's this Gouy-Chapman model from 1942. This contained one idea: the ions have a finite size. And if you introduce a finite diameter of the ion, you come up with an entropy term which looks like this. Then the mathematics of this can be handled. The only important point is that it has the excluded volume effect for the ions in this case only, because the solvent is still modeled as a dielectric continuum. And this effect is important at high charges and at high concentration. So the history of this is a bit funny. It has been rediscovered at least 3 times, one in 2007, And in 2008, it was even published as a FISREF letter. And I've seen it again in 2021 for some different case. But yeah, so it's a popular model. Yeah, of course, you go and then you set up the Euler equations and you put in Poisson. And there's one parameter which enters, which doesn't enter into the Gouy-Chapman. This is the radii of the solvated ion. This enters in the combination of a to the power of 3 times the concentration of the ions in the bulk. And here you see some capacity curves for 2 different values. And you can see when this phi 0 is comparatively high, you get this rather funny shape for the interfacial capacity, which is also being called a camel curve because it, yeah. But if this is lower, you get a bell-like curve. All of this was for concentrations which are high because this is the interesting part, right? The important point is obviously here the interfacial capacity goes down, and it goes down because of the finite size of the ion. So this is a nice feature in this model. But if you look at the values that you get for the interfacial capacity using a normal radius of a solvated ion, and you can, then you would have a radius of the order, I don't know, 4, 5, 6. But even then, the interfacial capacity is far too high. Of course, you can then go and change it, and you can also put some variable dielectric constant in. But there's no physical basis for using a variable value of epsilon. So this is an artificial model. Of course, one of the difficulties that the discrete solvent model is missing. So only the ions are being treated as particles with a certain size. And it's popular for ionic liquids because there the solvent is missing. You only have the ions. And so all of the important particles have then a finite size, which can be accounted. And in this case, it works much, much better than for an aqueous solution. And what I've drawn here is the case of an aqueous solution. So there are other models, but the difficulty is always, well, it's sort of similar to quantum mechanical DFT. There's a proof that a correct functional exists, but there is no method how you can construct it. So you have to start from approximation. You have to start from guesses. You have to start from your intuition, and this makes this a little bit difficult to believe in this. But there are approximate terms for the interaction of hard spheres, which seem to be quite good. There are terms for correlations, a bit doubtful, and there are many applications to side effects. This in particular when you come to confined spaces, and later I'm going to show you briefly an example of this. And a short overview of this method with many citations given in this comparatively recent article by the Sanlang group. And once again, the advantage is it can be combined with DFT, all of these versions, and it gives you then a model for the whole system. And as always, the interface is the problem, how to model the interactions there. Okay, this is an example for the classical DFT with hard spheres for the case of an ionic liquid within the pore, which in this case is taken as a cylindrical pore. This is the capacity plotted as a function of the pore width, and you can see oscillation in the capacity. And what always happen here is when you have 1 layer of iron, 2 layers of iron, 3 layers of iron, and 4 layers of iron, when just one of these layers can fit in, interfacial capacity goes up, and then it goes down again as you make it wider till the next layer can come in. Quantitatively, this is then certainly correct, but I don't think it's very profound, to be honest. But it is nice that you can see this in such a model. Yeah, one important model which is popular is a lattice model. And where you have all of your particles within the box, or you have them on a lattice. Typically, you use 3 different particles, cations, anions, and solvent. You can set them up on such a lattice. And this can also be mapped onto a certain variance of the Ising model. So the mathematics, once again, are comparatively simple. And this here would be a plot for a certain charge. We have the ions, we have the counter ions, which go to 0. And this would be the potential. But this once again has the wrong shape, that I'll show later. And you get this interface capacity curve, both of the camel and of the bell type. And you can then guess under what circumstances you're going to see a bell, and under what circumstances you're going to see a camel. But so this is nice from a quantitative point of view, but of course a bit simple if you really want to know what the double layer structure looks like, but it is useful. Now I come to work with a little bit data from 1980s, but which I still like much. And I hope I can convince you that you can still learn something from this model. And this is called Jellium in contact with an ensemble of hard sphere ions and dipoles, which was developed at the same time by 2 groups, by Henderson and myself, and by the group headed by Jean-Pierre Bardiali. So the solution is modeled as an ensemble of hard spheres. And there are 3 types of hard spheres. There the dipole moment, which is the solvent. You have one with positive unit charge. You have one with a negative unit charge. And we have to put them in contact with the metal, to which I can come later. The important point is that, that the statistical mechanics of this ensemble of 3 different types of spheres in contact with a hard wall. This can be solved in an approximation called the mean spherical approximation, unfortunately only for small charges. But still, the calculations are complex, and I think it was a major achievement that this could be made. And I think today there are few people who would be able to do this kind of calculations, which has to be done with integral equations. So, yeah, one of the things which you can plot is you can plot within this model when the excess charge is not too high. You can plot the distribution of the potential close to the surface. The plot here is for the simple case where all 3 particles have the same diameter, and you can see first at the drop of the potential, there's an overshoot, then there are oscillations, goes up and down, and this line here, this is the line which you would get from the simple Gouy-Chapman theory, which means that in this model, the electrostatic potential oscillates about the average value given by the Gouy-Chapman theory. And of course, what you see here really is something like a packing of hard spheres against a hard wall. This has been discovered in 2015 as overscreening, because you have this overshoot of the potential here. And then one of the nice features is that you can have an analytical expression, and you can develop within this model the inverse of the capacity as a sort of power series in K, where K is the inverse of the Debye length. And this is the first term here, which is the dominant term when the Debye length is large, because then K is small. This is the Gouy-Chapman term, right? There's a second term here, which is the next term, which is the power of K to the power of 0. So it is independent of the Debye length. This is something which people normally would call the Stern or the Helmholtz capacity. Let us see what this looks like. This has 2 terms. This is the diameter of the ions. This is the diameter of the solvent. And epsilon is a dielectric constant, which for water is 80. So you can see the first term here is going to be small, because this is going to be divided by 80. And this means that the nature of the ion should not matter much for interfacial capacity. as long as there's no specific adsorption of this ion. This is found to be true experimentally. There's a second part, which contains the diameter of the solvent. And this is the important part because you have epsilon, epsilon minus 1, and they practically cancel, right? So this is one, that there's a quantity which enters, which comes out of the mathematics. This is related by the dielectric constant of the solvent and is determined by this equation here. And this takes on for water, value of 80, a value of 2.6. Now, if you look at this, you can forget about the epsilon minus 1 and the epsilon. This then looks like the inverse capacity then for a capacitor with a dielectric constant of lambda. So this looks like a local dielectric constant of the order of 2.6, but it does not have this. It doesn't have the physical meaning. This is nothing but a boundary effect, and the value comes out of the mathematics and not out of a model where the dielectric constant varies. So this is one of the nicer features, and these will be the dominant term. And if the concentration is very high, you get something which is proportional to kappa. Then, of course, you must put the metal into the picture. And at this time, the only DFT version which one had was for a simple model called Jellium. And this consists of a simple picture where the positive charge on the ions is smeared out into a positive background charge like this. So it drops abruptly at the surface. But then you have the electron gas. And for this, you have all of the usual quantum mechanical interaction, exchange and correlation, in this case within the local density approximation. So this is very similar to the DFT of today, only the ions have been smeared out into a positive background charge. So at that time, we said, okay, this is going to be a model for a nice polycrystalline electrode. And important feature is, because of their small mass, the electrons spill out over the surface of the metal. You have the spillover part here. You have a deficit of electrons here. So you have a negative excess charge here, positive. So you have a dipole moment at the surface. The direction of the dipole moment is such that it keeps the electrons in. And this dipole moment makes an important contribution to the work function because it keeps the electrons in. If you use such a metal then for the work functions of polycrystalline SP metals in the vacuum, you can see that you get the right order of magnitude and you get the right trend. This means that here the concentration of ions electrons becomes higher and higher, and the work function becomes higher and higher as the electronic density gets higher. And so this is the sort of a result, the sort of an understanding which you can hope to get if you put this into a double layer model. So if you look a little bit closer at the density profile of Jellium, you see there's something which is called the Friedel of the oscillations close to the surface. These are plots for two different densities of electrons in the bulk. It would be the case where the density is low, then the oscillation is somewhat larger. Here the density is higher, the oscillations are somewhat smaller. An important point is what happens if you put an excess charge onto the surface, which is the same thing as putting an external field. You can see that depending on the sign, if you put a negative excess charge in, then the electrons spill out further. And if you put a positive excess charge in, then they sort of withdraw. And there's a certain position which is called the effective image plane. And this means if you put a point charge at a certain distance from the surface, it'll feel the image force, but it will not feel the image force from the metal surface, which is the Jellium edge, but as if the image plane were at the effective image plane. This is a certain distance in front of the metal surface. We can take another look at this. This is a distribution of the excess charge only, right? So we put an excess charge. You can see the largest part of the excess charge lies outside of the jellium, lies in front of the jellium edge, and you can calculate the position of the image charge simply as the centroid of all of the excess charge. In this case, you get the position which is here. So this would be the position of the effective image plane. Now, if we come back to our double layer capacitor, the position of the effective image plane is also the effective position of the metal surface in terms of the capacity. So this behaves like a capacitor whose surface is not at the real surface of the metal, but a capacitor which is at position of the effective image plane, where it's a little bit in front. And this shift, of course, makes the capacity larger because it makes the effective separation of plates, effective separation of charges, somewhat smaller. So yeah, and then the contribution of jellium can be thought of as a change of the dipole moment with an external field. The change in dipole potential, of course, opposes the external field, and hence this jellium or this response increases the interfacial capacity. And during the last decades, the contribution of the metal has been rediscovered as a quantum capacitance, but usually not for metals, but for substances like graphene or graphite or nanotubes, to which I'll talk a little bit later. So if we put this extra term in, this is the expression which we get for the inverse of the Helmholtz capacitance and the properties of the metal and in terms of the effective position of the image charge. And we have performed calculations. This would be for the capacity, the inverse capacity and potential of the ion charge for the SP metal. This is the curve which we get from our model. And our model has no single adjustable parameters. The only thing that enters are the diameters of the solvent, really, dielectric constant of 80, and then the density, the bulk density of electrons within these metals. And considering this is such a simple model, I think it explains quite well the overall trend. It's explained why capacity on mercury is so low, on gallium is so much higher, on zinc is so much higher. So when we got this in the late 1980s, we were quite happy with this. And I think the important point is that it explains something. What about charge electrodes? All this nice work for the ensemble of H2 and dipole really works only close to the potential of zero charge. But if you put in the dielectric using a Langevin function, there's a unique interpolation between the value and the potential of zero charge and the value when you have complete dielectric saturation. And so there's nothing to be fitted here. This is the expression which you get, and these are the curves which you get, right? So this here would be something like mercury, and this would be something like silver. And it is, and at least qualitatively, I think it explains what happens. Now I think it's time for a short break. I think I've been talking for more than 1 hour. And this was, of course, all the end of the 20th century. So we have a 5-minute break, and then we shall return to the 21st century in double layer theory and double layer models. Okay.
Thank you so much, Wolfgang. I think we're open to questions. So I'm letting the audience ask questions if you have. And maybe in the meantime, I can start. So in one of the last slides that you're showing, I think it's slide number 52 or 53 with the image charge.
What?
53.
53. Yeah.
No. Yeah, I know that in the field it is a big question as to how to put the image charge within the system. So I was wondering if you can comment on that. Is it a problem for metals, or is it most of the problem for semiconductor electrodes or electrodes that have a low density of states?
DFT has problem with image charges, right? Because the functional in DFT is local or semi-local at best, right? While the image interaction, of course, is a long-range part. So one has to be a bit careful on how to put this in. Within the calculations which we did at that time, this was not much of a problem because we calculated from Jellium the effective position where the image plane wind is, and we put this into our formula. So there wasn't much to worry. But if you have a model where you want to model everything by DFT, the metal and all of the solution, then there's a little bit of the problem with the distribution of charges because of the local character of the functional of quantum mechanical DFT. And of course, there's a problem for semiconductor also because there the bilength of semiconductor typically is much larger, and this is something which is difficult to handle if you want to use something like DFT. But then you can use the usual sort of classical model for semiconductors, and then you can put this in an intelligent way. So, yeah.
Okay. One question that I see, maybe you can explain or comment on the relationship between the potential of zero charge, the PZC, and the open circuit potential, how they are related for a metal.
The open circuit potential is simply what you get. You set up your system, you shut off your potential state, and then you measure the electrode potential, right? This is called the open circuit potential, and usually and conceptually, this has nothing to do with the potential of zero charge, because when you put a metal in contact with some solution, there's always something which is going to happen. You're going to have the specific adsorption of ions, and something comes up. So this is typically far from the potential of zero charge. Potential of zero charge is something which is a little bit difficult to get, and the best way is still to measure the capacity at low concentration of ions and look for the minimum in the capacity, and this should give the potential of zero charge. Now, there are two different concepts.
Right, so PZC is more of a flatbed potential.
Right, yeah.
Mm-hmm. I see a question from Maria.
Thank you very much for your talk. I have a question related to the double layer at the negative electrode. So in many of the models, how is it represented that we have solvated cation in the proximity of the electrode surface? Mm-hmm. And I wonder whether there is any difference if we consider the case where there are no other cations except of protons.
Yeah, I shall talk about cations and the value of cations a bit later, because protons are really small, right?
Yes.
And then they're, of course, they're not naked, right? They're always in the form of a Zundel ion of an eigen. But of course, they can get very close to the surface, and for them it's comparatively easy to get absorbed if there's some interaction with the metal. Later, I shall talk about the other alkali ions, and there's a difference between the small ions like lithium, sodium, and the larger ions like cesium, which I'm going to explain later. And this has to do with their solvation properties.
Mm-hmm. Because I see in many experimental works, which are sometimes compared with theory, for example, we take a look at the cations at the millimolar concentrations, but meanwhile, the pH is also, for example, around 4, which it means that we have also protons at millimolar concentrations. But in many cases, they are kind of not really discussed that much. So that's why I was wondering whether you think they should be considered in this case, and whether there are any special considerations related to that. But of course, if you're going to discuss it in the next part of the talk, I will just wait.
But I think it is important because then you have a competition. Protons at the surface, and then the other ions that are at the surface, right? And you must account for this competition. Experimentally, I think it's also difficult to keep the pH in front of the surface constant.
Yes.
There's difficulty, right?
Yeah, exactly.
Interpretation difficult also.
Thank you very much.
Thank you, Katerina.
Yeah, thank you. I have a question regarding your, or actually not regarding your model, but rather regarding to what you say about the model. You're unhappy about calling the interaction of the ions with the platinum surface special. But in the end, don't you think that there is something special in the sense also that all ions seem to interact with platinum much more strongly than with any other surface, and that secondly, we do not see any difference between different ions on the surface, which for silver, for example, you showed the plots, we can find different ions where the slope ranges from 1 to 0.6, where for platinum, all slopes seem to be very similar. So could you maybe comment on that?
Yeah, of course, typically adsorption on platinum is much stronger than say on mercury or on silver, right? And I think the fact that you see similar slopes is that you are within the range where the adsorption is so high that the Parsons&Zobel slopes, they are all small, right? While if you
why would you argue that the adsorption on platinum is always higher? I mean, platinum is often a very good catalyst, but a good catalyst is usually characterized not by the strongest adsorption, but by the ideal adsorption. So why would platinum always have the strongest adsorption?
Particularly if you go to platinum, there's no real double layer in the sense where there's no specific adsorption of ions. There's always something happening. You have OH minus, you have the other anions, whatever. There's always something. This is a very reactive surface. But of course, the interaction, say, with other metals like nickel, there the interaction of nickel with the solution is of course higher, right? And they are particularly only with much difficulties will you be able to find a certain region where nothing happens. But I actually was present when Kolb did his and Kolb and Pakoshi, when they did their famous experimental work on the double layer capacity of platinum 111, and then this famous value which you see of 30 microfarad per square centimeter. And this came out of a model where they had measured the interfacial capacitance, and they had 4 or 5 elements within the equivalent circuit. And it was also based on a model where you could really question a bit what actually happened, and they had specific adsorption within this model, right? The model which they used to get this value was one where specific adsorption was just a bit slower, and then they could separate that part of the capacity which came from adsorption from the part which was the usual metal part, right? And then they got this value. So platinum is particularly difficult system, and but I think that the effect that you see is simply a case where you have the adsorption of ions, and on platinum it is somewhat stronger. That's the reason why you see this very low slope in the Parsons&Zobel plot. And of course, once the slope in the Parsons&Zobel plot, once the slope is so small, it's difficult to see if it depends on the nature of your ions, right? Because it's going to be small in any case, it has to be larger than 0, right? So there's not much of a range over which it can vary.
Yeah. So, but there is a reason why there is nothing that interacts less strongly for some reason. And I think in principle that the interpretation that you are giving here is very much in line with the interpretation of the original paper and also the 2 follow-up papers. I think there's not so much of a difference other than maybe the word special, which one can debate about.
Yeah, okay. Yeah, perhaps, yeah. Yeah. The main point is that using this comparatively simple model, which we had proposed in the 1980s, we could explain the main effects, the deviation, Parsons-Zobel slope, and then the fact that the capacity was higher than predicted by the Gouy and Chapman theory, which is
that is in the models in those papers too, right?
Yeah, sure, right, yeah.
This is those models.
And I don't think we should discuss your paper
sure not. No. It was more about whether you really think there's something different, but then it seems to boil down that it is indeed that the ideas are the same and that there's not so much difference.
Right, yeah.
Thank you.
Okay, thank you.
Thanks, Katerina. Daniel.
Hello, thank you very much. You mentioned ionic liquids, and I'm curious to know if a great deal of work has been done in studying the electrochemical double layer where you have a concentrated electrolytes in this way.
Yeah, this is a very fashionable topic. I shall only in passing mention it because so much work has been done on this. And you can find more on this topic in this review article, which I'd mentioned at the end of the talk. I shall give a list of the order of 7 or 8 papers, and you can see ionic liquids treated extensively in 1 or 2 of these review articles.
Thank you, that's much appreciated.
Thank you. I think we can continue, Wolfgang.
Okay. So we go back to, where was I? Okay. Good, so we go back to the 21st century. And yeah, within the model which I'd shown, all of the metal was simply modeled within the Jellium model. But of course, you can calculate the effective position of the image charge. You can calculate this by DFT, then for particular metals and for single crystal surfaces. And this we have done for a couple of metals. We have done this for silver 111. This is the order of the order of magnitude for the position of the effective image plane in front of the metal of the surface of the metal. And if you put this for silver in, you get a value which is practically the same as the experimental value, but this is a bit of luck, I must say. We have the same thing for gold, and the surface polarizability of gold is somewhat lower because of the character of the D-band. We get a value which is a little bit slower, and the experimental value is larger. But of course, gold is also special because you have surface reconstruction of gold, which makes the interpretation of double layer capacities a little bit tricky. For platinum, we get 41. The famous Kolb-Bakoshi value is 30. I think the important point is you can make the sort of model better by using DFT and do calculations for specific metals, specific surfaces, and the values which you get are of the correct order of magnitude, and they can explain the trend. It explains why it is so much higher on silver, lower on gold, and well, platinum it's somewhat lower. So this helped in the understanding, and also we wanted to contrast metals with carbon structures, particularly with graphite, which is an important electrode material. And the next thing is to contrast the behavior of metals with the behavior of graphite. And the same thing you can do for graphene. You can do it for carbon nanotubes also. So an important point is graphite is a semi-metal. If you look at the electronic density of states of graphite, it is practically zero at the Fermi level. Then it goes up on both sides, and it's very much lower than the electronic density of silver. This gives rise to a special behavior. So we have put an excess charge. In the upper case, we have put this on silver. This behaves very much like the Jellium model, which you have seen, right? We have here the excess charge is right at the surface. The larger part lies outside of the surface, and you can calculate the position of the image charge, which is somewhere here. This is completely different once you go to graphite. Here we have a large penetration of the outside field toward the interior, and you see all these oscillations of the excess charge as a function of the position. You can then also calculate the effective position of the image plane, but while on silver it lies outside of the metal, this lies actually inside of the metal when you go to graphite. So here the effective position of the image plane then as a function of the charge. And these are the metals which we have seen. When you go to negative charges, then the overall charge on the surface is then a bit higher. We meet the position of the image plane also shift a little bit more outside. If you go to graphite, then the position has firstly, the values are always lower than 1, lower than -1 angstrom, meaning the image plane lies inside of graphite. Then the worst case is when we are at the potential of zero charge, because then the density of states at the Fermi level is then practically zero, which makes for a terrible capacitance. But then as you shift away to either side from the potential of zero charge, the electronic density at the Fermi level gets higher because it gets shifted, and then the capacity goes up, and it goes up in such a fashion. Okay, we can combine this with our ensemble of hard sphere ions and dipoles, and without fitting any parameter. These are the capacity curves which we get from our theory. These are the experimental curves which were taken from a paper of Gericher. And you can see also the large difference in the interfacial capacity between something like graphite, which has values of the order of 3 to 4, or perhaps a bit higher, and then the value for silver 111, we were at 70 at the potential of zero charge. The reason being that in the case of graphite, we have a penetration of the outside field into the bulk, or into a large surface layer of the electrode surface. Okay, let us change the topic because there are several other methods which we briefly want to cover. This ensemble of hard sphere ions and dipole, this had been handled by a certain type of integral equations, and this topic has been advanced, and there are now somewhat better versions of the integral equation technique. And a popular one is called the single reference interaction site model. And I don't think I shall go into the details of this, but this is also based on a compared to a simple model using integral equation techniques. And you have a finite size of the ion, finite size of the solvent within this model. And an advantage is if you want to, you can put in interaction of the particle with an electrode surface, which you can calculate by DFT. So part of the interfacial properties in a certain sense can be obtained by DFT. Well, I've worked with a specialist on this topic, and we had convergence difficulties when we wanted to solve this integral equations. But it seems that this Japanese group, which I'm going to mention in a second, can handle this better. Yeah, and like I said, a nice panel can be combined with DFT. This is a nice paper from the Botani group, which explains this well, how this works. And it seems to be nice what comes out. The important point is you can have a finite size, you can put certain interactions into your model, and you can learn something about the interface. And you can also use this then to actually look at reactions. Well, we had looked at this in 2010, so a comparatively simple version. Like I said, the difficulty is there was difficulties with the convergence. I first wanted the calculation to be done at 10 to the minus 3 molars, and it didn't converge. Didn't converge at 1 molar either, but it converged between 10 to the minus 2 and 10 to the minus 1, and one can learn something, but it was not as nice as I'd hoped. But there is this advanced version which seems to be much, much better. But you can look at certain things within this model, right? And this is water at the potential of 0 charge in contact with gold in this case. You can see that the oxygen interacts somewhat stronger with the surface than hydrogen does. So the peak here is somewhat higher. There are oscillations which are caused by the size of the particles and then how the water is structured within the surface. And this, I think, comes out more or less in the same way in any kind of model which has a finite size for the solvent, finite size for the ions. We're going to look at the distribution of the ions. In this case, we had sodium ions, which in the simple model kept from the surface, but we had specific adsorption of chloride ions. So we had a large peak here at the surface. This is certainly correct from a qualitative point of view. From a quantitative point of view, I would have my doubts. So let's look at simulations, and they are the classical, the DFT-based, which I shall only cover briefly, and there are recently some quantum classical, which I think the method is quite nice. So the classical simulations are based on a semi-empirical force field, and they are practically always done for the solution, right? There's a whole collection of such force fields, and they have been tested for decades, and they usually work well, at least for the bulk of the solution where they have been tested. Sometimes you have to calculate the interaction of your particles with the electric surface from DFT, because you cannot find them within the force fields. But of course, this can be done, and of course, the validity of what you get will depend on the quality of the force field that you use. But like I said, these typically work well for the bulk, and one hopes that they're also going to work well for the region which is close to the surface, and you might have to do something to get interactions with the electrode surface. But let's see what comes out. What can we actually learn? Distribution of water, distribution of the potential, distribution of ions, right? So, and there's one thing which I like particularly, which is the potential of mean force for the approach of a particle to the electrode surface. Say you want to study the reaction of an ion at a metal surface, say the deposition of a silver ion on silver. An important problem is what happens as you take the ion from the bulk of the solution toward the surface. How does its free energy change? Because certainly its solvation will change, and of course there's also the change in the interaction with the metal surface. I think this is a nice feature where the most important part you can get from classical simulation. I'm going to show you some examples later. Much of the early work was done from the group of Spohr, and this is one of his earlier papers. And this is mercury that in contact with 32 ions of sodium chloride, 400 water. Concentration is then comparatively high. For positive excess charge, you can see obviously then you have a comparatively large concentration of the anions go to the surface. The cations keep at a certain distance, and the water follows more or less the electric field that it sees around it. So then one can look at details. This is for the case of an uncharged surface, and here the The full line are for the cations, which are not specifically adsorbed, and this dashed line here is water. You can see that the maximum of for the cation is always between the maximum for water, right? So means the ions are sitting between layers of water. You can see this happen for the next 2 or 3 oscillations also. But this is different in the case of the specifically adsorbed anions. They have a large peak right at the surface. They carry a little bit of water with them, and then they more or less do their own things, right? Which tells you something about what happened at the surface. One important thing is there was this flip-flop model, which I didn't like. So one question is, how does the orientation of water change as you change the charge on the surface, right? This is for an uncharged surface, and the interaction of water, in this case, I think mercury, is such that the interaction of the oxygen end is somewhat stronger. So here you have the oxygen points a little bit more toward the surface, but you can see this is nothing like the flip-flop model, which had been advanced, right? So if you're here at minus 9.9 charge, the value of the cosine is still about 0.5, and only when you go to 1, you would have either a flip or you would have a flop. And I think this is one of the nice features that shows out that thinking in terms of flip-flop doesn't work. Yeah, there's a distribution of water, of oxygen and hydrogen, and once again, oxygen likes to be somewhat closer than hydrogen, which is what one typically sees. You see this in DFT also, I'm going to show you later. This is the distribution of the potential at the potential of zero charge, and you have the oscillation in the potential, which is simply due to the finite size in this case of water, right? And once again, one has oxygen attracted toward the surface, which means that at the surface we have an overall dipole potential, right? Which is of the order of 0.7. Yeah, this was with platinum and water. And now to one of my favorite topics, which is the potential of mean force for the approach of the reactant toward the electrode surface, which gives you the free energy as a function of position. This is important when you think of the overall path which a reacting particle has to take. And within the theory of Marcus, this would correspond to the work term. Only in the case of Marcus, we're thinking about outer sphere electron transfer, which means that the reactant always stays at a fair distance from the metal surface. So within the theory of Marcus, for outer sphere electron transfer, these work terms are comparatively small, but they become very important when you look at the deposition of metals, right? Because you take a silver ion right to the surface of silver, and the solvation changes. So, or what happens if you take a divalent ion like copper 2 towards the surface? This must be important what happened. And there's a technique from which you can get this, which is umbrella sampling, which you find covered in all of the textbooks on classical molecular dynamics or classical Monte Carlo. So let us look what happens. We wanted to look at the deposition of metals, and we were particularly looking at silver, and this black curve is for silver. We've always set the value equal to 0 in the bulk because we wanted to look at changes. You can see as you bring silver to the surface, nothing much happens. Here it goes a little bit up, then it actually gets a little bit lower than the value in the bulk, which means that silver likes to be a little bit closer to the surface than in the bulk. Okay. Same thing happens if you look at other monovalent ions of zinc plus, which would be an intermediate in the deposition of zinc. We'll also take the monovalent ion right towards the surface. There's even a minimum here and not much happen. But if you take a divalent ion towards the surface, you can see up the break of the solvation shell, right? This has at least 2 or 3 shells, which you can see. So Here goes to first maximum, second maximum, and here when it gets closer, then it really goes up, and it starts to lose its primary solvation shell. So this tells you something about the difference between the ions as you go to the surface. And an important question is, why is the position of silver and also of zinc right close to the surface so favorable? So we looked at how the ion is positioned there. And this is silver at an uncharged silver surface sitting within its solvation shell, right? And of course, it has lost a bit of solvation here, but it has this nice solvation shell here. Now, now one must think of solvation as a competition between hydrogen bonding of water and the interaction of the ion with the solvent. Now, when the silver gets to the surface, then the number of water surrounding it, of course, gets somewhat smaller, but the hydrogen bonding of water becomes weaker because water has less water that it can hydrogen bond to. And then it seems that in this case, the interaction of ion and solvent gains a little bit over the hydrogen bond formation. So here there's a fair number of hydrogen bonds broken, which is comparatively easy because there were few bonds to break. And so it has this nice cage where it feels comfortable. And that's why it has a small dip when it goes toward the surface. Yeah, okay, we did this for a couple of divalent ions. Copper plus just behaves like a little bit like silver, a nice minimum here. And of course, copper 2 goes up and up because of the break of the solvation sheet. And in this case, we could show that copper first has to go from copper 2 plus to copper plus, and then it can be deposited. Zinc is a bit tricky. We have a special paper on this, but I'm not going to talk about this because it's too complicated. Yeah, then we have the alkali ions, which have already been mentioned briefly during the discussion. And typically they do not absorb from aqueous solutions. And there was nice work from Graham from 1950s, but of course he showed this for mercury only. But even if we look at silver and at other metals, there are no signs that they do absorb. However, it seems that the nature of the alkali ion has a strong effect on a number of reactions. For example, on oxygen reduction, and this always takes place at potentials which are positive of the potential of zero charge. So in this case, it is clear that there cannot be any specific absorption of these cations on the electrode surface, but obviously they're close to the metal surface, and it seems that the nature, probably the size of the ion, seems to matter. So we wanted to understand what happens as we go through this. There are other reactions where it's important, ethanol oxidation, reduction of CO2. So, like I already said, in hydration, we have a competition between the hydrogen bonding and electric field of the ion. There's the famous Hofmeister series, goes back about 1 century, and he distinguishes between structure-making ions and structure-breaking ions. If you go down this series, then the borderline would be roughly between the sodium ion and the potassium ion. What does this mean? These ions here make their own very strong solvation shells, right? So they make their own structure within water. And these ions, they are too large, their field is too weak. The only thing that they actually do is they break up the hydrogen bonding structure of water. That's why they're called structure breaking. And so the behavior changes in a systematic manner as you go from here to here down the Hofmeister line. So we looked at the potential of potential of mean force of this ion. All calculations are for the potential of zero charge. And here we have on the left-hand side, we have the 2 structure-making ions, which make their own strong solvation shell. You can see as you bring them toward the surface, lithium, of course, is small. So the rise starts somewhat later, but it has the strongest solvation shell of all, so it goes up. Then there's a small secondary minimum here, as a couple of water has been stripped out of the solvation shell, and then it goes up and up and up. Right. Similar way is the behavior of sodium, but a bit weaker. It's somewhat larger, so the rise starts somewhat sooner. And since the solvation shell is not quite as strong as it is in lithium, then it doesn't rise all that much. It has a secondary minimum here, where the configuration actually is very much like that of silver, which we had seen, right? This nice cage at the surface, but this is not quite as favorable as, say, the coordination within the bulk, because the strong coordination has been broken. These are then the structure break-in ions, and they come toward the surface, they pass over a maximum, but then they have a minimum, which is practically the same value as in the bulk. These are the structure breaking one, because there's not much of a solvation shell to break up, and they simply break the structure of the solvent in the surface, and they break it at the surface, and they break it in the bulk also. You can see that a little bit if you look at the radial distribution function of the solvent with respect to the ion. And let's look here at lithium. And this is the radial distribution function in the bulk, and when it's at its local minimum. And there's not much difference, because lithium really likes to keep its solvation shell, and so there's not much of a change here. But this is different when you go to the structure breaking one, cesium, and there the radial distribution function is lower when it is in the bulk, so it is somewhat looser structure within the bulk. Of first peak here, then it goes down, but it is sort of squeezed when it gets towards the surface, and that's the reason why you have a second minimum here. The sort of squeezing helps to bring the energy down, and it is almost like in the bulk. So maybe this sort of behavior can be useful to understand what happens within the catalysis, what is called the catalysis through non-bonding interactions of these alkali ions. Yeah, then we have the quantum mechanical DFT, but there has been this nice lecture about those, so I'll not say much about this. Only the first work, which somewhat seems to be neglected, was an early work by the group of Prof, and he investigated with DFT structure of water at a silver 111 surface, which was a good choice. And this distribution of oxygen, which is the first nice peak, the second peak, and then it gets a bit noisy, because computer time at this time was much shorter and much more expensive than it is now. And just like in the other work, he sees in the distribution of water, he sees oxygen stays somewhat closer than hydrogen, and there are some oscillations as you go toward the surface. Now I want to come to look at the dynamics, what happens within the double layer. I mean, Judy always thinks that electrochemical processes would happen at a constant electrode potential, because we have the potential start, which keeps us fixed, right? And now people who try to calculate a free energy curve for a certain reaction, the usual procedure now is to keep the electrode potential constant at each point as you calculate such a barrier. But of course, this would mean that the response of the double layer to any reaction that happens is infinitely fast. But this is not so. That's called something the double layer relaxation time, which is of the order a little bit less than 1 nanosecond, and which I'm going to show that the double layer relaxation time is much lower than the typical time for an electron, for a proton transfer to take place. So we'll look a little bit at the time dependence. This is a nice work, a paper. It's about the relaxation of the double layer, and as in this case, an electron transfer reaction takes place. And the important point is the relaxation of the double layer is 2 to 3 orders of magnitude slower than, say, the transfer of a proton, not to mention the transfer of an electron, which is almost instantaneous. So this was the system that they looked at, and this is their setup. So in their model, the solvent was a dielectric continuum, and then the ions were soft spheres, and then the ions follow what is called the Langevin dynamics, which takes into account the friction which the ion experience as they move through the solution, where they actually undergo something like a Brownian motion, right? And so what they did, and they have one special position here, which is meant to mimic a redox couple. So at first the charge is empty. They do their MD for the ensemble of ions. At a certain time, they suddenly put an extra charge onto the center, and then they look at what happens to the relaxation of the potential at this position, which is the relaxation of the double layer of ions. And this is what they get. So this is the time at which they put the extra charge onto the redox couple. This is the change of the potential at this particular redox couple as a function of time. You can see it takes of the order about half a nanosecond before this has come to a constant value. And here I quote the authors. They notice that double layer relaxation is much slower than the electron transfer reaction, and somehow this ought to be put into the theory of electron transfer reaction. And even today, this is missing. Now, does this only happen for electron transfer, which is particularly fast? No, we shall look at what happens during proton transfer reaction, and this is some recent work from us. And we have looked at the molecular dynamics of the desorption of a hydrogen atom, which is absorbed on graphene. Such a hydrogen atom is in a metastable state. So by a very small part of charge, you can get it to desorb. You can look at the dynamics of the desorption, and this is what we have done. So it goes from an adsorbed hydrogen to a solvated proton within the solution. And we have used something called a DFT-based tight binding model, which is much faster than DFT, but all the interaction of the particles, they have been taken from DFT. So this is what our system looked like. We have two of these layers of graphene, and we have an adsorbed hydrogen atom here, and we have a lot of water here. At a certain time, we put a positive excess charge here. The positive excess charge here means that the average orientation of water is going to change, that the oxygen comes somewhat closer, and at some time, one of the oxygen atoms of water comes so close towards the hydrogen that it simply picks up the hydrogen and falls in an H3O+, and then it undergoes water steps. So let's simulation run. There, hydrogen gets closer, and now you see water steps happening, goes from there to there, and so let's look at the time scale over which this happens, and this is the time scale in picoseconds. And let us look at some of the distances. This here is the distance between the oxygen, which is going to take up the hydrogen, and the adsorbed hydrogen. So at first it's somewhat large because the oxygen and water floats around here. Then at a certain time it gets closer to the surface, simply picks up the adsorbed hydrogen, and then it goes on as an H3O+. You can look at what happens to the adsorbed hydrogen, which is the red curve. it's sitting here happily on the surface of graphite, but then it gets picked up by the water which comes, and then it leaves with the water toward the bulk. And all this happens within the time of the order of 0.4, 0.5 picoseconds. So about 10 to the 2 to 10 to the 3 times faster than the double layer relaxation time of water. Okay, we can look at the charges also. Here we have the extra charge of +1 being put into the system. At first, this charge is all on graphene, and then the water comes toward the absorbed hydrogen. They start to interact. The charge on graphene goes down. Then you have the actual reaction taking place, and it comes down, and the charge on graphene goes to 0, and the charge on the combined H plus water goes up towards 1. And all this within of the order of 1 picoseconds or a bit less, depending on how you choose your time scale. You can look at the potential within this region also. And let us first look at the curve when you only have water and the two sides of the graphene. You get a nice symmetrical curve. Right, this is the case where you have one extra charge, so it goes down, and you have oscillations due to the orientation of water. The important plot is what happens when the proton transfer takes place. What does the distribution of the potential look like? And you can see here it oscillates, and it is very much different from that which you had at the beginning, which means that you have a change in the double layer potential as the proton transfer reaction takes place, and it looks nothing like the relaxed state. And the final state would be this green curve here. We have water plus one proton in the solution. The extra proton is somewhere here, so it's not quite symmetrical. Important point is that you have a sizable difference in the potential at the time where the proton transfer takes place, and at the final stage where you have once again the equilibrium of the whole system and the relaxation of the double layer has taken place. So proton transfer occurs at a fraction of a picoseconds, much faster than the double layer relaxation. So I think it is not wise to calculate the free energy curves, keeping the double layer potential constant, because keeping a constant takes place on a much longer time scale than the actual reaction takes place. So I think the interpretation of these curves, which have been performed for constant electrode potential, has been taken with a certain grain of salt, because they do not correspond to that which happens during the reaction at the time scale in which the reaction takes place. So briefly, I shall pass through some other things because time is getting late. The latest one is, which I've seen, is a nice mixture of quantum mechanics with molecular mechanics. Of course, quantum for the electron. Typical point is always the coupling of the to a system, and I think this is the paper which perhaps you might like to read. And the system was well chosen for silver 111 in contact with a solution of sodium fluoride, and they observed the absorption of F- at high positive potential, which is to be expected. The one feature which I find somewhat strange, they claim to see a phase transition at very negative potentials, where they claim to have a place exchange between the sodium ion and water on the surface. But obviously, for a phase transition to take place, this must occur in a concerted manner, which I found a bit difficult to understand, and perhaps this has to do with the finite size of the ensemble. Because if you look, say, at silver, do not see anything here, which would give you an indication of a phase transition taking place, which would give rise to a discontinuity. But I think the method as such is nice, and it's one of the methods which probably is going to be used more within the future. Yeah, one point which I always find a little bit difficult, if you use DFT or a similar method, it's always difficult to define the absolute value of your electrode potential. And if you look at the definition, if you go to the Casati papers, you need the change in the potential as you go from outside the solution toward the inside. And then one has a dipole potential right at the surface of the solution, which is caused by a net orientation of water right at the surface. But if you do this with a molecular dynamics simulation, then the structure which you see at the surface, of course, looks nothing like the structure which would have on normal water, but it is in equilibrium, say with air. So what one gets here for the change of the potential as you pass through this layer, I think this has little to do what happens when you have a real surface of water, because the structure here is nothing like that of normal water. And of course, the water here is going to evaporate if you let your molecular dynamics run longer, no? So this also has to be taken with a little bit of grain of salt. Okay, briefly through special topics. Nanoslits and nanopores are nice because the ensembles are small, and you can use DFT, quantum mechanical DFT with some advantage, or you can use classical simulations also. One point to bear in mind: these systems are usually in contact with the bulk electrolyte. We have an exchange of particle, and this occurs at constant electrochemical potential. And then the method to use is a grand canonical ensemble for all the particles which can be interchanged with the bath. They would typically be ions, electrons, and the solvent. So an easier method to use than MD is the grand canonical Monte Carlo, because it is easier to put particles in and take particles out. Yeah, one nice effect which has been discussed, when you are in such an nano slit or in such a nanopore, then most of the ions are very close to the surface, and then they see the image interaction with the surface. And that means if you have two ions sitting in front of a metal surface, usually if in the absence of the metal, they would interact through a strong 1/r law. But when they're close to a metal or to any conductive surface, then you have the image charge, which is on the electrode. And this then changes the 1/r interaction to 1/r cubed in interaction, which makes the interaction between ions much weaker. And this allows for a much denser packing of ion than if you were within the bulk. And this nice effect has been called the super ionic effect. This is the key paper in which this has been considered. Yeah, and ionic liquids, like I briefly mentioned, is an important topic. And there's much work being done, and the difficulty is that the ions are bulky. You can argue a little bit about the unique classical interaction potentials which are being used, and there are some convergence problems because the whole system is viscous and the dynamics is slow. But this is an interesting system, and this is a large field, and much is being done on this. And of course, the number of ionic liquids which you can study is very, very large. And typically, they have a cation which is small and an anion which is large. So this makes for some difficulties, but it's interesting. And then there will be a topic which has dropped a little bit out of fashion is interface between two immiscible solvents, liquid-liquid, and there used to be a model which was simply 2 times the Gouy-Chapman Stern model, right? You had the interface between the 2 liquids here, and then you had one Stern layer here, second Stern layer here, and then you had 2 Gouy-Chapman-like layers here. And this is not popular with several people. But well, when I was on a sabbatical with my colleague Silver in Porto, he had looked at a lot of systems, and he showed me this plot of the Gouy-Chapman theory, or capacity of the Gouy-Chapman theory with respect to the experimental values for a fair number of systems. And yeah, and at first I didn't know what to make of this point because it was difficult to see any kind of order, right? But then I noticed something which was strange because, with the exception of this point, which is an experimental error, I suppose, all of the points lie below this line, which means that the capacity is larger than that predicted by the theory of Gouy and Chapman, even though the concentration was of the order of 2 to the minus 2 molar. Now, if something like the Gouy-Chapman Stern or the Neeson model were true, the capacity would have to be lower than that predicted by Gouy and Chapman, because you have this certain range in which the ions cannot enter. So obviously there was something wrong with this simple modified Neeson model, because this would predict the capacity which is lower, because no ions can be found here. And we came up with another thing what the system actually looks like. The interface between the 2 liquids is rough. It's not a sort of straight line. So the ions can get much closer than you would think, right, within this, and this makes the capacity larger. We have an overlap of the 2 double layers on each side. And if you go through the mathematics, you can see this makes us larger than predicted by a simple Gouy-Chapman theory. Okay, let us sum up. There's no universal double layer model. They're usually weak, and there's nothing like a flip-flop as a child change, but there's a gradual change in the orientation of water as it changes. And an important point is that each ion is different. Its distance of closest approach depends on how well it fits into the structure of water, if it's a structure making, if it's a structure breaking ion, and of course, if it is chemically adsorbed. So that's the reason why it is impossible to make a universal model. And there are a variety of methods which you can use and models which you can use, and each of them has its own strengths and weaknesses. And so briefly, some advice. Now, if you want to work on double layer theory, my advice is don't. Don't unless you have a very new and bright idea, something which nobody has thought of, because so much work has been done that if you want to have an impact on the field, you must have something which is new and bright. And of course, it should be something which does not involve months of computer time, right? Because then it gets boring and the novelty gets somewhat lost. If you have to work on aspect of double layer theory for certain reasons, because you want to look at a certain reaction, so you want to understand oxygen reduction and the effect of cations, then of course you have to look at the problem at hand. And if it's simply the strong adsorption of metals, then simple DST of the sublet and of the adsorbate should be sufficient. But you are out of luck if there is a strong interaction of the adsorbent with the solvent, which can be through partial charge or dipole moment of the adsorbate, and sometimes even due to hydrogen bonding. Then you must put water into the calculations, otherwise it is not realistic. And really what you had to do is to put in explicit water and then perform MD, but this is costly in terms of time and computing power. But it seems to be the only way out. There's a nice paper by Karen Chan and her group, and she showed that using implicit water does not help much. So if you really want to get quantitative answers, you have to use MD and implicit water. And of course, adding one layer of water, which at T equal to 0 would be ice, does not help either. If you want to look at distribution of particles and of potential, then typically classical MD augmented by DFT is a nice method to use, because for most particles you have interaction potential, which are nice. And one point is for multivalent ion, it seems that image charges are important. If you have univalent ion, this typically get screened by the surrounding water. But when you have a doubly charged or triply charged ion, you have to look at the image charges. And there's a nice paper from the Sulpizi and Heinz group, which shows a nice way of how you can put this in. If you want to look at the effect of particle size, there are several things you can do. You can use classical MD, you can use the integral equations, or you can use the classical DFT. Classical MD is comparatively simple, but for these there's no sort of ready-made software which you can simply use. You either have to ask one of your colleagues to help you out, or you'll have to write it. So in this case, you would usually go for classical MD, but it's sort of standard. In confined spaces, I think it is nice. You can use either DFT-based MD, or you can use grand canonical Monte Carlo. And important to put the image interaction with the wall in, because you get reading spots. So some final wishes from my side: do not use simple geometrical models like the Gouy-Chapman stern or whatever. Do not talk of the inner and the outer Helmholtz plane, and I think this is also oversimplified. Yes, and please don't show Gouy-Chapman stern model in your paper. It has been shown so often, and this is known not to be a very good model of the double layer. Please do not use a locally variable dielectric constant, because there's no physical ground on which you can base this. Of course, you can put it in and simply use it to fit to data, but then it doesn't help much. And please do not write another 100-page review article on double layer theories. I've had to read too many during the last couple of weeks. Okay, thank you. That was it. I got funding from DFG, Volkswagen Stiftung, NATO, and DAAD. There's a short list here, but if you look at the latest review article, which has just come out, he has of a couple of 900 papers which he cites. So if you want to find any paper which I have not cited here, you can look here in this article. And this also contains a lot of citations. Or both of them have appeared in chemical reviews. So finally, let me thank a couple of people. And I would first like to thank Douglas Henderson, with whom I worked on the ensemble of Hartz IV and dipole and Jellium during the 1980s. Unfortunately, he died last year, one of the things that happen as you get older. But it was a very nice cooperation I had with him. And the same was true for with Jan-Pierre Bagnali, who worked with Lesser Bloom on the same model as Douglas and I, and we had some fruitful competition at that time. I want to thank Ezekiel Lever, who also worked with me on the ensemble of Hartz IV and dipoles, and particularly on the Jellium side of the model. Paola Quino, who did all of the calculation for the potential of mean force at the ion come towards the surface, and then Elisabeth, with whom I share all of my science and all of my life. Okay, thank you.
Thank you so much, Wolfgang. It's an amazing talk. Thank you. So we are open to questions. Again, we have an open question session. Let me see, maybe I can start. If we go to the slide number 93, I think it's when you discuss the desorption of hydrogen from a graphite surface. I guess it was a modal system in some way, right? So my question is, do you view it as a more of a non-adiabatic reaction from an electronic transition point of view?
No, I would think from an electronic point of view, this is an adiabatic reaction because the electrons, the electron simply follows the configuration of the cores, of graphite, hydrogen, and water. And as soon as the oxygen of the exactly water is sufficiently close to the hydrogen atom, and then the electron transfer starts to take place. And if I go back a little bit, you can see this here as they come close enough. You can see the charge on the graphene or the graphene goes down, and the one on the H3 plus goes up, goes to H3O plus, and this all happens within a very, very short time. I would say this is typical for an adiabatic electron transfer following the course of the heavy particles.
Okay, so it means that in principle you don't have to treat proton as a quantum particles. You don't have to look at proton tunneling in this case, as you would probably do for a non-adiabatic cases.
I don't think there's any evidence for proton tunneling to happen within these system. I mean, how could the proton tunnel? Right, it would have to. I mean, when you have a distance between maybe. Right, you have the oxygen at first here, and the proton which is here cannot simply tunnel through about 1 angstrom layer of water, or 1 angstrom layer of nothing towards the water, and the water must be in the correct orientation for the supposed tunneling to take place. I think it's much simpler for the water to come somewhat closer, and then they start to meet, and you have the electron transfer.
Okay, and on that slide that you showed, I think it's a relevant question that I have a follow-up question, 93, where you showed so we see different variations in potentials depending on okay, so you have H3O. So if you go from Eiger to Zungel ion, does it really change it? So does it matter how big the actual cluster of water plus proton you have to include in the model?
Yes, of course. As the proton changes its position and it goes from Eigen to Zundel and from Zundel to Eigen or something else, you're going to see somewhat different shapes for this. This is the average which we have taken over a certain interval of time. Yeah.
I see. No, now it's pretty clear. Thank you. We're open to questions, please. Hi, Sue. I think you were first.
Hello, can you hear me?
Yes.
Yes.
Okay, thank you for the great talk. And I have a very basic question about the metal-water interface. Because I noticed most people only consider the orientation of water dipoles, but even in pure water, there are still like low concentrations of protons and hydroxides, right? So is it possible that they can be recruited to the interface because they are better at screening charge?
Yes, of course. If you have if you are in an acid solution, right, then the concentration of protons is comparatively high, and they can comparatively easily go to the metal surface. Now, the details depend on the strength of the interaction of that metal with protons or with hydrogen atoms, right? If you look at platinum, then you know that over a certain range, you're always going to have adsorbed hydrogen atoms. And platinum, the interaction being comparatively large, then this sets in at potentials which are higher than the hydrogen evolution reaction, this so-called UPD. If you look at others like silver and gold, the concentration of protons is probably going to be high, but over a certain range, they're not going to adsorb specifically on the surface of silver and gold because the interaction is weak. That's why they're bad catalysts for hydrogen evolution reaction. But I think the point that you made is important, but should not only look at the orientation of water and what water does, right? But also what the ions do. This is particularly true if you have some small ions and very mobile ions, like the proton or the OH minus.
Okay, thank you.
Thank you. Next question.
Thanks for impressive talk. Maybe I missed the point. I'm wondering regarding the adsorption of hydrogen over the graphene. I have seen the charges changes from +1 to 0 to -1 in your simulation. I'm wondering, is this charges related to the cluster or the full simulation box exactly here?
Yeah. But we started with a simulation box where there was no excess charge, right?
Okay.
And we simply let, so this initial system was what you see here. You have the 2 layers of graphene, you have 1 adsorbed hydrogen, you have all of the water, and the total charge is 0, right? When we now put an excess charge of +1 into the system, the excess charge always goes directly to the graphene, right? Because there are no states close to the Fermi level in water, right? So all of the changes in the charge which you make on the system, they always go to the graphene. So when you make the change in the charge here to +1, the charge goes to the graphene. It stays there for a certain time. This is an excerpt from a longer run, right? And only then when you see the water coming then closer to the adsorbed hydrogen, then you can see that the water picks up the hydrogen atom, and then the charge jumps to the H3O plus, and the charge on the graphene goes down to 0, because now you have the excess charge in the solution.
Okay.
And
Okay.
then in one of these forms, then you have the typical forms for protons, solvated protons in the solution.
Okay, I got your point. Yeah. And my another question that I'm just wondering to know some comments from you, because I have seen your seminal work on outer sphere reaction for the oxygen reduction reaction over the platinum. Yeah. I'm wondering that is there any connection with the concentration of electrolyte from changing the mechanism from inner sphere to outer sphere to generate the O2 ion over the platinum electrode?
You're talking specifically about the oxygen reduction, right?
Yes.
Yeah, and we have looked at cases like gold, where the interaction of oxygen with gold is very weak, and that is always in the outer sphere mode, because the oxygen simply does not get sufficiently close.
Exactly.
The interaction of the oxygen with platinum is of course stronger. You can get the O2 adsorbed, and then it would be predominantly an inner sphere, right? It would not go to solvated oxygen in the solution. That's the difference between platinum and
gold.
And gold. And silver behaves very much like gold. We have a paper on silver, and it's quite close.
Thank you.
Thank you. Wolfgang, I have also a question about the local dielectric properties or permittivity that you mentioned. So there are many experimentalists who studied in experiments of trying to obtain certain numbers. How do you see, as a theoretician, these attempts? Are they useful for the theory then? Probably then they're not quite measuring the actual dielectric constant, right? They're measuring something else.
Yeah, they actually measure something like an average property. Right, I've seen papers where they have changed the thickness of a layer of water, and then you apply an external field. Then you look at how this external field is being shielded, and then you put this down to an average value of the dielectric constant of water. Of course, you can do this. Of course, it also tells you that the screening of an external field becomes weaker as the layer of water becomes thinner. Yeah, which is obvious. But if you say this is due to the value of the dielectric constant changing systematically from 80 down to 6 or something, yeah, I think you are using a concept which does not have much of a physical background, because a dielectric constant is not a local property. Yeah, you must at least have a mesoscopic ensemble to define it.
I see. So are these properties that are measured in this case useful for the theory?
Yes, yes, yeah, of course, because you can you can see how the screening of the external field changes. Now, this could induce somebody to make a model for this for the system, in which he has some good model for water and something. He changes the thickness, puts on an external field, and then looks at how the screening of the field changes with the thickness. Right? So he could mimic this and see to what extent he can get something which agrees with the experimental data, and he could also perhaps find out that something has been missing. For example, if you have such a very thin layer, I think it matters what you use for the two electrodes, right? Because we have seen that the double layer capacity depends on the nature of the electrode surface. So if you do this kind of experiment, you must also think of the fact that there's a contribution of the electrode surfaces to the screening of an external field. But this is something which I could, if you do 2 or 3 cycles between experiments and theory, right? I think you could get something useful out of this.
Right, thank you. Katerina.
Yep, thank you. I have a question on your calculations on the potential of mean force, which I actually very much like. I just wonder, how sensitive are you to the exact parameterization of the force field, and then particularly to the ion parameters, but also the water-metal interface?
Yeah, right. Like I said, this is always a critical question, how good your parameter set actually is. Typically, we try out 2 or 3 and then see if this makes a difference. And we only publish if we are confident that the one that we have used works. Yeah. You compare to 2 or 3. All of them have been tested for decades. And usually it doesn't make much of a difference which one you actually use. But this is something that you have to check.
Even the water-metal interaction doesn't make too much of a difference.
In this case, we haven't seen much. Well, we have looked at gold, where the interaction is weak. We have also looked at silver, where it is weak. And yeah, and this is a parameter which we have calculated from DFT, right? We have used something, I don't know, 40 different orientations of water and with respect to the surface of silver, and then fitted this to a force field, and this seems to work.
Yeah, thank you.
Thank you. A few more questions that I think that maybe are really important to resolve, at least in my opinion, for the community. So when we move from, just a second, when we move from the metal electrolyte interfaces to something like a semiconductor interface, semiconductor-electrolyte interface, or it's typical for oxide electrolyte interfaces too, what really changes? So in terms of modeling, I know that people are trying to avoid this, but maybe you can make your own comments and give your own perspective on this direction. So it's, what exactly gets complicated?
Well, typically the die lengths of semiconductors are larger than the die length of electrolyte solutions. Mm-hmm. And that means that the largest part of the potential drop across the double layer is not going to be on the solution side, but it's going to be on the side of the semiconductor. And so you can use the space charge theory semiconductors to work out the capacity of these interfaces. There's only one critical point to consider. This is if you have surface states at the surface, which can get filled or can get emptied as you change the electrode potential. And this you somehow have to this you have to account for. But if they are not present, you can simply use the space charge theory of semiconductors to get the interfacial capacity, because in most of these cases, it's a semiconductor that is going to dominate the interfacial capacity because the stable length is much larger.
I see. So in terms of the actual drop of potential, you just need to sort of correct for the semiconductor side of the interface.
Yeah, exactly.
Okay. The other question is related to the explicit versus implicit use of solvents in calculations. So a lot of people use implicit solvent, and I know that you mentioned it in part during your talk, but maybe you can give a bit more on more insight sort of into what actually it can lead to, what kind of problems, what types of inaccuracies such modeling can end up with.
Yeah, implicit solvent is of course convenient, right? Because it makes your calculations fast, right? The models that I've seen, they're all a little bit artificial, right? You have special dielectric properties which change. Sometimes people put in a Debye length, which is very, very short. If you use such a model of, then the first thing I would check is simply take your electrode surface, put this in contact with the implicit solvent model which you use, and look what sort of capacity curves you get, right? How the potential drop changes as you charge your surface, and if this looks like something which you would see experimentally. And in most of the cases which I've seen, it does not look like this. Still, it depends a little bit what you want to investigate. Say if you want to compare various metals and see how good or how bad a catalyst they actually are. Now, if you always make the same error for the solvent, it does not matter for the order of the catalytic properties which you see, right? Because you will always have a certain offset in the error.
Right.
Then using a simple model can be useful, but there are other cases where it does not work. If you have something like the adsorption of OH, this typically has a certain dipole moment. Sometimes it even forms hydrogen bond with water. This is something which an implicit solvent does not model. Then I think at least you should put in one layer of explicit solvent, probably do molecular dynamics with it, and then mimic the rest by an implicit solvent. That will make the system better.
Okay. Okay. Related to also the intermediates and the adsorbates on the surface. So in electrocatalysis, often what people calculate is the thermodynamics of adsorption of intermediates that are not charged.
Yeah.
But in the actual reactions, we assume that they should be charged at some point. So the activation barriers should be related to the charged state of the adsorbates. The question now is how to go around it. Is it something that's solvable? So, or is it important?
I think it is important if these intermediate states are charged. And if you go to the nice paper from the group of Chan, which I have quoted, and they have shown that that in this case one really needs explicit solvent. Otherwise, you get something which is wrong. You get errors of the order of half an electron volt or something. And this is sort of error which is important for catalytic reactions. I think this is not easy solve this problem, unless you have lots and lots of computing times and you are patient and wait for a long time, and then you can put the explicit solvent in. But this is a tricky problem, and I wish there were a more elegant solution. But at the moment, I cannot think of a more elegant solution.
Okay. Then the last question that I have is very general. Maybe you can, as a theoretician with so many years of contribution to the field, you can give to the experimentalists a certain hint as to what we as experimentalists can provide more. So what is missing from our side for the development of the theory?
As far as
in general,
as far as reaction goes, it would be nice if there were more temperature-dependent studies where one would get the energy of activation and where one would get the pre-exponential factor also. I think this would be good for theorists to have, and theorists can try to model the reaction, and that is what many groups do, and then get the energy of activation, compare this with experimental data. And I think the pre-exponential factor is important also, because this tells you something about the dynamics on how this happens. And often the dynamic of the solvent which plays an important role. And these are questions which one can answer better if you have temperature-dependent studies.
Okay. Thank you so much, then, Wolfgang. It was a very great talk that I guess for many students it will be also very important, because this topic of double layer, in my opinion, it's somewhat smeared across the literature. You have to pick up a lot of things, put them together, and even in this case, we end up with a lot of mistakes. So hopefully this talk will be very, very
for the invitation.
Important. Yes.
And thank you for hosting this talk.
Thank you so much.
Thank you, and bye-bye.
Bye-bye.